Hey everybody, in this lesson we're going to look at inclined planes and trying to figure out the mechanical advantages. First of all, the inclined plane is a ramp of some sort that allows a weight to be pulled or pushed up it, and there's a mechanical advantage in using an inclined plane or a ramp. In this example, it's kind of a poor example. I found a picture on the internet. There's 2 pounds of weight. Looks like a round object that's being pulled up by a pulley. This is a fixed pulley. So a fixed pulley is going to be a mechanical advantage of 1. So what we have here is we have 2 pounds of resistance force being pulled up by 1 pound of effort force. So the question is, does the 2 pounds go up, or does the 1 pound go up? We are not sure yet. We don't know. So in this case, we have an inclined plane that's got a 40-foot length and a 20-foot height. Now, sometimes you have an inclined plane problem that instead of telling you what this angle is, this would be C in the triangle, they'll tell you what the base is. So if you know the base and the height, what you have to do is use Pythagorean's theorem, a squared plus b squared equals c squared, to come up with the length of this. But in this case, it already gives it to us, so we'll figure that out. All right, let's give you some information. The ideal mechanical advantage of an inclined plane is the length of the inclined plane divided by the height of the inclined plane. Now, in previous examples, we've been using the IMA as d of e over d of r. So by looking at these two equations, we already have some data here. We already know that d of e is 40, and because it's the length, d of e is equal to the length. And we also know that 20 is our height, so we already know what d of r is. So we know that since our inclined plane is pulling a 2-pound weight up 40 feet, and we know that the weight being pulled down is being pulled down 20 feet, we can kind of see our moments. Here's our moment of resistance, the height and the weight. And this is our moment of effort, the length and the weight here. So we got to set up our equation. So by going ahead and completing the IMA, we can see that we have a 40-foot length divided by a 20-foot height. So we have a mechanical advantage of 2 to 1. So the answer is, right now we're in equilibrium. The weights offset each other, and there is no mechanical advantage other than you're holding 2 pounds of weight up with 1 pound. That's a 2 to 1 advantage. So we could do the same thing with our forces. We could say 2 divided by 1, f of r divided by f of e should be 2 to 1. So we should have a 2 pound f of r divided by a 1 pound f of e. So now it's telling us, by doing our math and using these equations, which one of these should be the force of resistance and which one of these should be the force of effort. So we'll set up our equation. So in this equation, in this problem, we're confused. We don't know which one is f of r and we don't know which one's f of e. What we do know is we started out with IMA. We knew the length was 40. We knew the height was 20. So we went ahead and calculated d of e over d of r, 40 over 20, 2. Had a mechanical advantage of 2. So in this equation right here, this is how much we know. We know that the mechanical advantage is 2. So we know that the two forces we're using are 2 and 1. It's got to come out to 2. So we want to go, to 2 over 1. You can't put 1 over 2 and come out with the right answer, or it just won't be wrong. Right. So 2 over 1 is 2. We know that f of r is 2.